Hi, in this video we will explain the main points behind our study published in Oikos entitled The Role of Temperature Variability on Insect Performance and Population Dynamics in a Warming World. Despite of amount of research on the consequences of global warming on ecological systems, most studies examine the impact of changes in mean temperature in ecological variables. However, there are few studies concerning the role of thermal variability on ecological processes. It has been argued that these changes may unleash several responses at the population level, namely, latitudinal and altitudinal geographic range shift, changes in reproductive phenology, changes in body size, or temporal variability of population abundances. Considering the susceptibility of arthropods to thermal changes, special attention should be paid to the link between the ecological physiology of arthropods and their observed population dynamics. In the last few years, several authors have explored the consequences of the nonlinear relationship between body temperature and several performance variables, such as the intrinsic rate of increase, survival, or fecundity in ectotherms. Three basic scenarios have been proposed to understand the ecological consequences of climate change. In the first scenario, mean temperature will increase without changes in variability. In the second scenario, a change in the variance of temperature will occur without a change in mean. Finally, in the third scenario, both the mean and the variance of temperature will change. Here, we analyze how performance curves may change with alterations in mean temperature and variability, as a starting point in linking individual and population performances under different climate change scenarios. The relationship between environmental temperature and physiological performance has been described as a unimodal and asymmetric function. This type of curve will be our baseline or null model to examine the response of the intrinsic rate of increase, Rm, under the scenarios of global warming. Several characteristics of this curve deserve special attention. First, the lower and upper limit define which can be considered the niche amplitude of the focal species in the temperature axis. This limit are the points where the curve intersects the temperature axis, or the points where Rm is equal to 0. Below the lower limit and above the upper limit, Rm takes negative values, which mean the population is not viable in the long term. Second, the inflection points mark the points where the second derivative of the function is 0, or in other words, where the acceleration of performance begins to decrease. Finally, maximum performance marks the maximum Rm, and the projection on the temperature axis marks the optimum temperature. In our first scenario, that is, an increase in mean temperature without changes in variability, a population located between the lower limit and the point of maximum performance will react in a positive nonlinear way as a response to the increase in mean temperature. On the other hand, population between the point of maximum performance and the upper limit will react in a negative nonlinear way to the increase in temperature. In the second scenario, mean temperature does not change, but variability could increase or decrease. In this case, the effect of thermal variability on performance may be understood by analyzing the mathematical properties of the performance curves. Considering the symmetric curve of performance, the effect of variability under no other forces can be derived from Jensen's inequality. According to this mathematical law, between the lower limit and the inflection point, increases in temperature variability will result in a higher Rm. On the other hand, in the decelerating part of the function, between the inflection point and the upper limit, a greater variability in temperature will result in a lower Rm. Another interesting consequence of the effect of variability is the change in thermal limits. In particular, increments in variability imply that lower and upper limits shift to the left. In this situation, some unsuitable temperatures below the lower limit turn into suitable conditions, and some suitable conditions below the upper limit turn into unsuitable conditions. Another important consequence is that at any level of thermal variability, the maximum value of Rm will always be lower than expected under constant optimal temperature. This last result, along with the asymmetric change in thermal limits, lead us to the corollary that the area under the performance curve will always decrease with thermal variability. Finally, The last scenario predicts changes in mean temperature and in thermal variability. In this scenario, we combine the prediction of the two previous ones. Results show that between the lower limit and the inflection point, the effect of changes in mean temperature and variability is positive. Between the point of maximum performance and the upper limit, the effect of changes is negative. The area between the inflection point and the maximum is an area where there are mixed and opposing effects of mean and variability. In this area, an increment in mean temperature causes an increment in performance. However, the opposite is true for variance. Therefore, the net effect of a change in mean and variance would depend on the relative magnitude of the respective changes. A resume of our prediction is shown in this 3D graph. First, the limits of thermal niche will be different to those predicted under constant temperatures. Second, maximum Rm will always be lower than expected under constant temperatures, and the area under the curve is negatively related to variability. Third, specifically for species whose niche space is limited to some degree by thermal conditions, we can predict that a reduction in daily thermal variability could ameliorate the stress of individuals living close to the upper limit. On the other hand, under a scenario of increased variability, the predicted expansion to new habitats will be greater than the expansion without considering thermal variability. Finally, our analysis emphasized the importance of the link between ecophysiologists and population ecologists to link individuals, demography, and population dynamics under different scenarios of global warming. Details might be found in our Oikos paper. Also, a complete list of the publication from the authors may be found in Google Scholar or ResearchGate. Thanks for your attention.